Radio interfaces of GSM. Antenna radiates the electromagnetic waves according to the electric signals given to it. Electromagnetic propagates between the transmitter and receiver. Waves generate electric field in the receiver antenna as per the electrical signal sent from the transmitter. A radio interface is transceiver, transmitter and receiver of the signals. interface is a radio interface between the mobile station MS and base transceiver BTS. Interference means one signal modifying the other. The signals of same frequency band cannot access the medium at the same time. SDMA multiplexing. A method in which the same set of frequency components of the same range and at the same time slot can access the medium in different direction or cells. TDMA multiplexing. A method in which frequency components of same range in same direction or cell can access the medium in different time slots for the different radio interfaces. FDMA multiplexing. A method in which different set of frequency components of a frequency range are allotted to different radio interfaces and they can access the medium in same direction or cell and in same time slots. Space division multiple access SDMA. Assume that BTS-PQ with N-directed antenna covers mobile stations in N cells. Each cell defines a space. A given BTS covers the PTH cell and the cell is presently covering K mobile stations MS1, MS2 up to MSK. K can vary with time. MS can always change its location and move into another cell. There is space division multiplexing of the signals from the MSs. Figure shows SDMA from mobile station cell I and cell J using the same radio carrier channel CH and M in the same time slot. Time division multiple access. A set of maximum 8 MSs out of 1 MSs can be assigned a radio carrier channel by a BTS. Assume that cell I is presently covering 8 mobile stations, MS1, MS2 up to MS8. There is time division multiplexing of the signals from each set of 8 MSs. Figure shows TDMA from mobile stations in cell I using same radio carrier channel CHM in different time slots. An MS can use the same radio carrier channel CHM in one or more of the 8 distinct time slots, SL0, SL1 up to SL7, each of 577 µs. Data bus in a data frame. A set of data bits in a SL is known as burst. A set of 8 data bus defines a data frame. A mobile can send multiple data bursts within a frame. Each frame uses different channel radio carrier frequency. Half-duplet transmission. The transfer of a mobile device can function in half-duplet mode when the uplink time slot is at TU and downlink time slot at TD are assigned separately by a BTS and TU-TD is constant at 577 µs. Example. Consider 3 mobile stations MS1, MS2 and MS3 transmitting in a cell. How will the burst from these MSs be assigned in 8 time slots using same carrier channel CHM? Assume B1 assigned SL0, B2 assigned SL1, SL4 and SL7, B3 assigned SL2 and SL6. Assume B1, B2 and B3 the data bursts of MS1, MS2 and MS3 respectively. At an instant, a data frame can have bursts B1, B2, B3, X, B2, B3, X, B2 transmitted in 8 time slots SL0 to SL7 respectively. X represents unassigned slots for access by either BTSJ or other MSS that are using the same radio carrier channel. Since an SL is equal to 577 µs, data burst period is equal to 577 µs. Each data frame transmits in 8 into 577 µs is equal to 4.615 ms. Frequency Division Multiple Access FDMA. FDMA transmitter allots the available spectrum bandwidth by dividing into different frequency channels for communication by multiple sources, sets of MTS. Figure shows FDMA by mobile stations in cell I using different radio carrier channels. Frequency Division Multiple Access FDMA. A set of maximum 124 radio carrier channels, each of 200 kHz bandwidth, can be used in GSM 900 downlink channel, MSE to BSE, BSE to BTS and BTS to MS. 124 in the uplink channel, MS to BTS, BTS to BSC and BSC to MSC can be used. Each channel transmits data frames of 4.615 ms, 8 time slots each. The frequency slot for each channel is 200 kHz. A set of maximum 8 MSs out of /MSs can be assigned by BTSJ, a radio carrier channel frequency for uplink. Downlink frequency is greater than uplink frequency of a radio carrier channel by 45 MHz. The 124 frequency slots in GSM 900 in the uplink frequency range, channel 1 890.1 MHz plus or minus 100 kHz, CH2 890.3 MHz plus or minus 100 kHz and so on till CH124 914.9 MHz plus or minus 100 kHz. Downlink frequency slots CH1 935.1 MHz plus or minus 100 kHz, CH2 935.3 MHz plus or minus 100 kHz and the last frequency is CH124 959.9 MHz plus or minus 100 kHz. A GSM system station is permitted use the CH2 to CH123 only. All the BTSs taken together can communicate over 90 channels, CH0 up to CH89 available in GSM band. Total number of reserve channels can be 32 for the data transmission of mobile service provider. Frequency hopping in data frames. Hopping means changing a channel for a set of 8 MSs. A data frame frequency channel assigned to an MS by the BTS can be changed to select frequencies at a certain rate according to a predetermined sequence. This helps in ensuring better signal quality for most of the period. GSM hopping rates are 207.6 HOP/s. Specific frequency values result in signal fading during propagation. Do not provide expected signal strengths at the receiver's end during transmission. Format of a data burst. There can be variable delays during transmission as the reflected signals take different amounts of time. Original signals can be reconstructed using a digital signal processor DSP, but the DSP spends computational time in processing the signals. Total 148 bits are transmitted in a data burst. 114 bits are user data or control data. 6 bits, 3 at the head H and 3 at the tail T, both are called tail bits TB. At H bits at the beginning 000. At T bits at the end 000. 26 bits in the middle of the burst are transmitted as training TR bits. The TR bits enable the receiver to synchronize using H, TR and T bits and select the strong components of the signals. Division among 142 minus 26 bar 2 equal to 58 bits, each after H and before T. Data in the burst can be of two kinds, MS data or mobile service NSS control data. On either side of the TR bits, an S bit can be placed to specify whether the source is the MS or NSS control data. Meaningful data bits are 57 after H and 57 before T. Division among 57 bits, each between H and TR and TR and T. Assuming that only one time slot used in a data frame of 8 slots when transmitting voice, and assuming that the only data bursts are voice data bursts. Total 114 bits, 57 plus 57, for the user data in a data burst time slot. Traffic multi-frame. Total 26 data frames in one, in which there are 1 control data, 1 empty and 24 user data frames. Traffic multi-frames transmit TCH, FACCH and SACCH data. 12 slots for user data. User data is followed by 1 slot for control data signals. Therefore, only 12 out of 13 data bursts are used due to need for frequency correction and synchronization bursts. The voice data user data rates are 12 by 13 into 24.7 kbps equal to 22.8 kbps. This is when only one time slot is allocated for use in a data frame of 8 slots. Traffic multi-frame transmits in 26 into 4.615 ms equal to 120 ms interval. Has just one data burst for control data out of 26. Data control channel rate is 1 divided by 26 into 24.7 kbps equal to 950 bps. Interleaving in a traffic multi-frame. Interleaving means inserting in between. The packets, each consisting of 456 bits in a 20 ms time slot, are interleaved in a traffic multi-frame for voice traffic. Figure shows interleaving of data from the mobile stations in a traffic multi-frame during 120 ms interval. Example to show how two mobile stations interleave data in the traffic multi-frame. Assume two MSs, MSI and MSJ multiplexed in TDMA slots data bursts. There are 57 bits after H and 57 bits before T in the data bus. TCH by F, traffic channel full rate, transmission rate is equal to 22.8 kbps. Therefore, there are 456 equal to 8 into 57 bits per 20 ms in voice traffic from 2 MSs. When 20 ms packets of MSI and MSJ interleave, then all the 57-bit time slots after H in each data burst are used by MSI and all the 57 bits before T in each data burst are used by MSJ. Interleaving distributes the effects of channel characteristics variations with time on multiple MSs. 4 types of control data bursts. Different type of control data bursts are required as follows. Access grant channel AGCH, synchronization channel SCH, frequency correction channel FCCH, dummy burst. Access grant channel AGCH. The call setup takes place when setting the initial connection using a burst called access burst. The channel in which this burst is sent is called AGCH, access grant channel, a part of CCCH, common control channel. Synchronization channel SCH. The TR bits help the receiver in correcting path changes. All the MSs that are communicating with the BTS must be synchronized. The total time durations of forward and return paths vary as some MSs are closer than the others. A timing advance required for synchronization when a BTS receives a signal from a far-off MS compared to a short distance MS. Synchronization burst is used. SCH, synchronization channel. The channel used for this burst, a part of BCCH, broadcast control channel. Frequency correction channel, FCCH. A deviation in the frequency of a radio carrier may occur. Interference with the neighboring channel frequency is also possible. During synchronous data transmission, the receiver must synchronize the clock rate according to the incoming data bits. Frequency correction burst from the BTS helps in correcting the carrier frequency. In place of TR, S and user data bits, a 142-bit sequence between H and T is deployed. FCCH, frequency correction channel. The channel for this burst sent a part of BCCH. Dummy burst. When no useful burst being transmitted from an MS or BTS after the connection setup, then a dummy burst is transmitted. Traffic and control data channels. If the transmitted data is not correctable at the receiver, it's blocked for further processing. Traffic data channels. Voice coding using a codec, coder, decoder. A codec circuit codes analog signals into digital signals and decodes digital signals into analog according to various coding and decoding algorithms. The error correction bits, cycle redundancy check (CRC) and redundant bits appended and data interleaving is performed. 3 types of voice traffic. Voice at full 13 kbps, half data rate speech, enhanced full rate speech. User data or subscriber data is also called traffic data. Different types of voice traffic. TCH/FS, traffic channel / full rate set for transmission. TCH/HS, traffic channel / half rate set for transmission. TCH/EFR, traffic channel / enhanced full rate set for transmission. TCH/F14.4, traffic channel / full rate at 14.4. TCH/F9.6, traffic channel / half rate at 9.6 kbps. TCH/F4.8, traffic channel / half rate at 4.8 kbps. TCH/FS, voice coded with a codec, coder, decoder at 13 kbps. Additional bits appended after coding, the data rate is enhanced to 22.8 kbps when transmitting at full speed. TCH/HS, coded with a codec at 5.6 kbps and after the error correction bits, the data rate is enhanced to 11.4 kbps and transmission takes place at half speed. The available data rate is 22.8 kbps. Advantage is that double voice signals can now be transmitted. However, this sort of voice rate results in degradation of voice quality. TCH/EFR, coded with another enhanced coding technique employing a codec. EFR gives an enhanced voice quality but has limited error correction bits because the data rate is limited to 12.8 kbps. Advantage is that the voice quality upgraded in those cases where the transmission error rate is small. A codec may function in automatic mode and code the voice as TCH/FS or TCH/EFR depending on the transmission error rate detected in the bus. TCH/F14.4, TCH/F9.6, TCH/F4.8. Due to large number of subscribers at a base station, the GSM specifications provide for the traffic rates of 14.4 kbps, 9.6 kbps and 4.8 kbps also. Control data channels. The 184-bit packet from data link layer is formatted for the data bus bits. The 184 bits are added with 40 parity bits, 4 tail bits and 224 half convolution coding bits. Total result in the 456-bit packet, multiple of 114-bit in a data burst. There are 4 formats for control data bursts in data frames. Can also be formatted as 456-bit packet with different coding procedures than in traffic multi-frame. Various types of control channels: CCH, DCCH, dedicated control channels; BCCH, broadcast control channel; CCCH, common control channel; DCCH, dedicated control channels. An MS sends TCH traffic only after a call setup. A bidirectional communication channel present between the BTS and MS before the TCH traffic starts is called standalone DCCH, SDCCH. SADCCH, slow associated dedicated control channel, used for the registration, authentication and other requirements. Total 782 bits are sent as dedicated control channel data in 1S in case of slow associated standalone DCCH, SADCCH. 950 BPS can be sent as a control data slot in a traffic multi-frame. FACCH, fast associated control channel with TCH. When more than 782 bits are to be sent per second, then the TCH part of the data burst can be used. Then DCCH is called FACCH, fast associated control channel. BCCH, broadcast control channel. A BTS needs to broadcast the frequency and cell identity. A BTS needs to broadcast the information regarding frequencies and sequence options for hopping that can be assigned to the MSs in the cell to all the MSs. BCCH is used for this purpose. Enables an MS to get an available radio carrier frequency channel and transmit with different frequencies on different hops and synchronized with the BTS. The synchronization and frequency correction bursts also use the BCCH. CCCH, common control channel. A BTS, when granting access to an MS so that MS can use either SDCCH or TCH, uses a channel called AGCH, access grant channel. After the access is granted, the call setup or call forwarding can take place. The control channel used for such purposes is called a CCCH. When call setup requirements are transmitted from the MS, CCCH is called RACH, random access channel. RACH. Data burst format during 577 µS in place of the H user data, S TR, S user data and T sequence. A 145-bit sequence is modified as 8 H bits, 41 synchronization bits, 36 bits user data and 3 T bits, total 88 bits. The guard space-time intervals are now equal to 68.25 into 3.692 bar 2, equal to 126 µS before H and after T bits. PCH, paging channel. When call forwarding information transmits from the BTS, the CCCH is called PCH. Control multi-frames. A control multi-frame, 51 data frames. A control multi-frame transmits in 51 into 4.615 ms equal to 235.4 ms. A traffic multi-frame transmits in 120 ms. Superframe. After formatting, a superframe can have 51 traffic multi-frames of 120 ms each or 26 control multi-frames of 235.4 ms each. A superframe therefore transmits in 26 into 235.4 ms or 51 into 120 ms, both equal 6.12 s. Hyperframe consists of 2048 superframes. Transmits in 2048 into 6.12 s equal to 12,533.76 s equal to 3.5 hours. Sequence numbers s equal to 0 to 2048 into 26 into 51. 1 slots in a hyperframe is assigned to each 4.615 ms data frame. S encrypted along with the data so that after decryption, the original frame number can be recovered for sequential arrangement of data. Since the frames sequentially transmitted through the 8 TDMA time slots, the S also helps in identifying the original time slot of a given